Space Flight Center. He's a scientist in the Earth Sciences division. He's been involved in numerous atmospheric projects, both in terms with ozone depletion, stratospheric processes. And today he's going to share with us, he's won, I left all my papers in the car. He's won countless awards for NASA. He has over 150 publications. And it's our great pleasure to welcome him to share his thoughts and some information about the future of NASA Earth Science mission. Mark, thank you very much.
Thank you. Switch on this. I'm trying to find it. There it goes. Okay, can you hear me? Yes. Okay, great. Well, it's really nice to come back to my Iowa State University, where 39 years ago I started out as an undergraduate. Seems like an ancient time. This is before computers. But we had to go to the library if we wanted to do research. Now we just go to the internet. And I'm too lazy to go to the library myself. So I'm going to talk about NASA and what NASA does in Earth science. And I think that it's always a surprise to people that we actually do Earth science at NASA. We have a big program. It's over $1 billion a year is spent at NASA on Earth science and Earth science missions. And I thought I'd talk about what we're sort of looking at now and what does the future hold for these missions. We have a lot of missions in the works being planned to study the Earth from space. I'm going to kind of go over the whole problem here. Now, this is a new thing for me. I've never used one of these before, so let's see if this works. Okay. So why does NASA do Earth science? We provide satellite and sensor technology development for all the agencies that use satellites to measure the Earth, and principally NOAA. So all the GOES spacecraft, when you look at the Weather Channel in the morning, they show a picture, either infrared or visible picture of the Earth. That technology was developed by NASA and provided now as a turnkey operation. We launch that rocket, we launch the satellite, we monitor its performance, and then we turn it over to them. We also are developing the new NPOS polar orbiters, which are going to be launched around 2000 as a series for NOAA about 2012. It's an integrated DoD NOAA program. They've merged the old DoD program with the NOAA program as a cost-saving measure. It's a really great idea. GOES-R, which is the next generation of GOES satellites, the geostationary orbiters. And we also provide measurements that fall between the cracks. We look at do some measurements just because no one else is willing to do them. And historically, that's been column ozone amount. NASA is, in the Clean Air Act, in charge of the ozone layer, so to speak. And another quantity that I'm going to talk about a little bit is total solar irradiance. It used to be called the solar constant. So the amount of energy output from the sun, but Congress wanted to wonder why we kept wanting to measure a constant all the time, because it was constant. So we had to change the name to total solar irradiance. NASA is also a core agency in the President's Climate Change Science Program, which is CCSP, and we're supposed to be providing input into the climate change policy that's sort of the head in the sand policy that we have currently in this administration. And we also link our Earth science programs with universities like Iowa State and other universities. We have vast amounts of data that come down from the satellites, and we need a lot of help. We just can't do that all. So we send a lot of money to universities to help us through programs, peer-reviewed programs. So what is the main science question that we hope to answer with satellites? And I think it all boils down to climate, 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 to paraphrase the realtors, location, location, location. And climate change is a big issue both from the political arena, as you see the people fighting over Kyoto, and also it's a concern to everyone. One of the most common questions we get asked of the government is, how is climate change going to affect my backyard? And with a climate model with a resolution of 500 kilometers by 500 kilometers, that's kind of hard to answer that question. When we can say things like, well, global warming will be 2 degrees or 4 degrees, it doesn't tell you anything about your backyard. And so that understanding the climate problem is really one of the main goals of our future science missions. And you can just see from this why this is such a concern. This is, I don't know if you can see this very well, but this is the past 140 years of the surface temperatures in degrees centigrade. And then this is the past 1,000 years, and you can see this part's compressed right up into here. This is from Science magazine. And it's, there's a lot of uncertainty and variability in this, which is the gray here, but definitely things are changing. And this is the volume of glaciers. Actually, it's the terminus of the glaciers in Europe, and this is the negative numbers, and this is in meters, why they're retreating. It shows that they're retreating very rapidly in Europe. And the volume in the last 150 years is a tremendous change. So something's happening in the climate system, and it's almost inarguable at this point. I mean, even people who have played a critic role, past like S. Fred Singer and others, are saying that global warming is taking place. They're not even arguing the issue anymore, it's the magnitude. So we've gotten past the argument that there is no such thing, but we're still not certain, tremendously certain, to the political satisfaction of many of what the magnitude is going to be. So, but the point I want to make is that climate is also always changing. If you go back a million years, the climate was very different, and there weren't people around that were changing it. So, what are the big issues is, how does the climate system work? What are causing all these changes? What are the feedbacks, both positive and negative? And how do we distinguish between natural change and man-made change? And this is an example of this is a sort of famous graph after Jim Hansen, another famous Iowan, who put this together for, I think this appeared in Proceedings of the National Academy. And it divides up the change in climate forcing since 1850. And these are in watts per square meter over here. And the zero line is along here. And the red indicates positive warming. The blue indicates cooling. And I don't know if you can see this very well, but this is CO2 and methane here. And these are, this is indirect effects of ozone and water vapor response. This is CFCs. Turns out that chlorofluorocarbons are a huge climate forcing, even though they're a very tiny part of their infrared spectrum is right in the middle of the window region, so it's just, they're really important. Tropospheric ozone, N2O. But one of the things I want to point to here is that these little error bars are some level of uncertainty. Well, why is the uncertainty in these greenhouse gases? Well, we can measure them. They're so long-lived that we can measure a single point on the Earth, we can measure the CO2, and we pretty much have what it is everywhere, because it's so long-lived. It's in equilibrium in the Earth's atmosphere, pretty much. On the other hand, one of the big issues is air. Whoops, did I do that? I did. Let me see if I can reverse it. Well, I think we're going the wrong direction here. Okay. The other big issue is aerosols. And you can see here that this is 2.4 plus or minus 0.3 watts per meter squared, and anthropogenic aerosols are 1.8 cooling, plus or minus 1 watt per meter squared. A friend of mine said that the political part of this number is here, the scientific part is here, and as long as this number is big, we all have jobs in the future. And I think that's pretty true with the case of aerosols. Why are aerosols so uncertain? Well, there's an enormous number of feedback problems with aerosols, but they're very short-lived. There's a lot of sources and sinks of aerosols. They live about 10 days. They're transported very far, so they're very much in tune with where they're forced, and there's lots of issues, and I'm going to talk about a couple of those in a second. And then there are natural changes like sun. So these kinds of changes are just direct reflection of radiation in space, which is cooling the planet, Then you have black carbon, which absorbs things, it heats, aerosol, which heats the planet. And then you have biomass burning, organic carbon, soil dust, forest cloud changes. This is the Toomey effect, where aerosols actually make clouds a little bit brighter, so they reflect more radiation. And then you have volcanic, over here in natural forest, you have volcanic aerosols, and the changes in the sun. This is the solar constant I mentioned earlier. It does change slowly. There's some uncertainty there. So why is predicting climate so hard? If you're thinking I'm going to get to NASA missions, I'll just wait. This is just the simplest model you can think of. This is a simple, if you go to any textbook on climate, they usually start out with a simple energy balance model. Okay, so you have a planet which is radiating in 3 dimensions in the infrared, and you have the sun, which is broadcasting energy outward, and you have this little circle where it's intercepting radiation. So you can make the simplest, stupidest model possible. You basically have the input, the solar I0, which is the solar constant, the solar flux, total solar radiance, times 1 minus the albedo. The albedo is a fancy word for the reflectivity, how much is reflecting back into space. So if the albedo is 1, it's reflecting everything back. And this factor 4 is the difference between 4 pi r squared, the surface area of a sphere, versus pi r squared, which is the intercepted radiation. And you make it equal to Beer's law, which is equal to sigma t to the 4th. So you basically, this is the radiation coming back out of the planet in the infrared. And you can calculate the temperature, and you get 255 degrees Kelvin, which is really cold. You think, well, wait a minute, something's wrong. Well, the reason that it's different from the average temperature of the Earth, which is 288 degrees Kelvin, is because of the greenhouse effect. We live with the greenhouse effect already. It's really warming us up. It's preventing us from having a planet which is really cold. In fact, this temperature corresponds to the temperature in which the planet is, the layer that's sort of just above where the greenhouse effect takes place, which is the tropopause. It's about 10, 12 kilometers up. And that's the temperature of roughly the tropopause. That's the radiation radiant temperature. So between the tropopause and the surface, the atmosphere is trying hard to get rid of the heat that's building up. And it's throwing it up through clouds and energy. It's trying to transport it toward the poles to radiate this energy away. This is the greenhouse effect, and it's really important for our planet. So people say, we don't believe in the greenhouse effect. Well, sorry, fellas, it's already here. And it's doing a good job on us. And so one of the things you can do in this little simple equation is you can just sort of ask yourself, here's the solar flux and solar constant, and here's the temperature, and you can sort of see with a fixed albedo what would happen. And you see a fairly steep curve here, temperature varying a little bit with the solar constant, not significantly, but moving up here. Now, what if you had a real planet, or even a simple model where you had the albedo change with temperature? Snows on this planet, this simple planet. Okay, so if it gets colder, it gets whiter. And if you do that and you start up in a normal thing, you find that what happens is you come down a curve like this and you go like this and you intercept the snowball Earth. Okay, the planet the albedo goes to 1 or 0.9 if you fix it like I did here. And basically you're stuck on this curve. And to get back into the normal plane, you have to go way up here off the screen, and it eventually pops over as the planet gets hot enough. So even this simple climate model, my point is that even this simple model, which is just a fixed or slightly varying albedo model, is quite complicated with multiple solutions because you get that t to the 4th there. So things are hard. And furthermore, now let's take a look at what's the actual thermal flux from the planet. This is an infrared measurement of the infrared radiation streaming away from the planet in watts per square meter. And look at how it varies. Okay, so what are we looking at here? We have warm, these are high values, these pink colors, and the blue is very low values. And what this is showing us is, first of all, we have Antarctica, which is very cold. So there's very little infrared radiation coming out of Antarctica. It's cold. You expect that. And out of the polar regions. Then you have, as you get into the tropics, yes, huge amounts of radiation coming out from the surface. But what are these things? Well, most of you probably recognize immediately as regions of high cloudiness, where clouds are coming up to the tropopause, blocking the radiation coming from the surface and radiating at this much colder temperature, which is the temperature of the tropopause. Okay? So that's what these regions are here. Okay? So even this simple model that I had doesn't even come close to resembling what the Earth has. It's a very complicated system. It even gets worse. Let's look at just systems which take a long period. We have to consider in climate change 50 to 100 years. Okay, so let's look at the aerosol issues. Okay, and this sort of summarizes all the problems with aerosols, and you can get yourself tied into a mental knot with this stuff. Okay, so let's just say aerosols. We have two kinds. We have sulfate and dust. They're actually fairly bright, and they reflect sunlight from the planet, and they cool the Earth like I showed you before. But they also make clouds brighter, which also contributes, amplifies that cooling effect. How do they make clouds brighter? When you have an aerosol, you have a preferred condensation nuclei. So that means the little water droplets in the clouds are a little bit smaller. And so when you calculate knee scattering, which is why clouds are white, they get whiter, they get brighter when you have lots of little small particles as opposed to a bunch of big raindrops. Okay? So this effect, sulfates and dust, make the Earth cool. And it's believed from my graph I showed you earlier, that has been balancing against global warming by the trace gases, CO2, N2O, methane, etc. So in the process of generating more carbon dioxide, we've also generated a lot more aerosols from power plants and things like that. And they've been balanced against each other. There's another kind of aerosol which we call black carbon, which is just a name for a carbonaceous aerosol or a dark aerosol. These aerosols absorb sunlight and they heat the atmosphere. They actually suppress clouds. They're up in the upper troposphere, and the clouds normally you have a hot surface, the hot heat rises, and you get a cloud, basically condensation. Warm summer day, you get that. If you have aerosols sitting up there, they're heating it, increasing the static stability of the atmosphere. And so the cloud doesn't form. You have fewer clouds. So these actually warm the Earth through fewer clouds, and they also actually heat the atmosphere. So these aerosols are going in the opposite direction. Both of these will produce less rainfall. This guy produces less clouds. This guy produces clouds with smaller water droplets and therefore less condensation. So we get less rainfall from these clouds. Well, this is a big problem for the hydrological cycle. Now we have loss of vegetation. Well, loss of vegetation cools the Earth. If you look at the Earth and you look at forest areas, it's very dark. Okay, they're absorbing a lot of radiation. Plants are dark. Okay, when you kill all the plants off, you have light brown soil underneath. Most places, except for Iowa, it's dark brown. But Iowa's rare. Okay, most places things don't grow as well. Okay, so this causes more loss of vegetation, causes more dust. More dust feeds back into the system. So you can see you can wind yourself into a knot on this problem. And this is why climate forecasting is really complicated. We're just starting to get a handle on this process, and I'll show you an example. This is satellite observations of aerosols. So here, this is a paper appeared by Corin et al. In Science in 2004. This is the Amazon basin, and this is a MODIS picture, which is one of the instruments we now have in orbit. And they were doing some biomass burning here. And these are days, they selected days which are very similar meteorologically. And so you have these sort of popcorn cumulus going on in a normal situation, but then when you have smoke, you can see there's no clouds in the smoke region. This is dark aerosol regions heating the atmosphere and suppressing the clouds. You notice also that this is a river running through here, and you can see there aren't any clouds on the river because the surface temperature is cooler at the river. You don't have the heating at the surface, and so you don't have the clouds over the river. So these are very locally produced clouds in a very sort of stagnant area. So you can see that this effect actually is working to wreck the clouds. So let's see if we can quantify this. And actually, this has been done. This is from Corin. You increase the aerosol amount, what happens? Okay, so you have these two effects here. We have effect of reduction of the clouds, and we get net heating. And we have an effect of increasing aerosols, reflecting radiation back into space, causing net cooling. So who wins? In this particular case, the heating wins. Why? Well, as we increase the aerosols, the clouds decrease. They're decreasing here, causing more heating. That is, the clouds are going away, less reflection from the clouds, more heating. Eventually, the clouds are all gone. So the energy is just coming right down to the earth. They're not being reflected in space. As the aerosols increase, they're, of course, cooling all the time. But the net effect is a warming. So you add these two effects together, you get a warming here. And it has this little notch here as a result. So the net effect of smoke is to cause warming when you take into account the cloud feedback effect. So you can see how this is a really, really hard problem to work out. It takes a lot of clever guys to figure this out. And this is based on observations with assumptions about what's called the albedo of the aerosols. They've done some different numbers in here. But in almost all these cases, except for very reflective aerosols, which are these dots down here, you get a net effect of the aerosols are actually, in this particular example, are actually causing a net heating of the system by cloud suppression. So where is NASA now with our Earth science missions? I've sort of set the stage to tell you a little bit, to give you a flavor of the kind of complexities of the climate problem and why we're really interested in it. Why we need a lot of observations to sort of work out this problem. So we've just completed launching the EOS series of satellites. The last one, the last big platform, Aura, which I'm actually in charge of, went up in July 15th, 2004. These are the three large platforms, big observatories. There's been two smaller platforms, SOURCE, which measures the solar flux, and ICESat, which is measuring ice sheet volume from space by using laser altimetry. And I'm not talking about these very much because they have lots of instruments on them, but these are sort of single instrument payloads. And then ocean scatterometer called QuickScat, which measures ocean roughness and winds. We've also launched a series of land remote sensing satellites, such as Landsat 7 in 1999, that's the new land resource satellite, EO1, which is an experimental satellite for technology development, and SAC-C, which is a satellite built by Argentina, which is a land resource satellite. We provided a lot of the technology for this one. Our instruments are on basically their spacecraft. And NASA is launching these Earth System Pathfinders now, GRACE 1 and 2, and that's a gravity mission. It's pretty interesting. I just want to take a moment. It's the first, we call it non-photonic mission we've ever launched into orbit. Basically, GRACE 1 and 2 are two satellites orbiting the Earth with a microwave link between them that measures the distance between the satellites as they go around. And the distance changes as a result of the subtle changes in gravitation of the Earth due to things like soil moisture. The ground gets a little more water in it, the gravity increases, believe it or not. If you have certain circulations on the ocean where the highs and lows, the gravity changes. And this satellite's sensitive enough to actually see that by looking at these distance between these satellites. And they can work out things that are going on sort of inside the Earth's crust or the upper levels of the Earth by looking at those distances, how they change. So this is the first really non-photonic, no photons involved, it's just gravitons. If they exist. Anyway, so later this year we're going to launch Calypso and CloudSat together. These are co-manifested missions. So this is a little movie. Let's see if it plays. So this shows all the satellites that I just mentioned going around the Earth that NASA has put up recently since 1999. You might recognize the tune. Who knows what the music is? What? The test. Okay, I'll give you a hint, it's from the planets, right? It's Neptune. Anyway, so here's EO1, Landsat, and SAC-C. These are in orbit together on the same path, making measurements together. Here's Aqua. You can almost not read these. And here's Aura, right behind it. And I'm going to talk about that in a minute. These two satellites are forming the ends of what's called the A-train, which we're assembling in orbit now. So these are the EOS missions. These are the other missions, GRACE, EO1 Timed. Timed is a space science mission. And this is pre-EOS missions that are still in orbit. And this will take a second to shut off. Come on. Well, let me try one more. There it goes. Okay, so this is what's next. What are we doing beyond this? Oops, I did that again. Let's go forward. Oops. There we go. Okay, so the first one I'm going to talk about is something called the A-Train. And that's 6 satellites in a constellation which is being assembled now in orbit. The first one was Aqua, launched in 2002, and the last one will be launched in 2008, called OCO, or OCO. Then I'm going to talk briefly about NPP, which is the new polar orbiters, GLORY, which is a mission to look at aerosols and total solar radiance. We're going to talk briefly about further out, Hydrus and Aquarius. These are soil moisture and salinity. We're going to measure ocean salinity from space. I think that's pretty cool. And the Global Precipitation Mission in 2008, which is, actually most of these are going to be around 2008. So we have a whole new set that's kind of coming up after this last one. So the A-Train is a series of satellites. They're closely lined within 15 minutes of each other. They all make measurements following each other. So what you saw was Aura and Aqua. Parasol, which is a CNES, the French satellite agency, was launched just recently, December 15th, I believe. And it's sitting up there now. It's just gotten into orbit with this group. And later this will be Calypso and CloudSat. And then in 2008, OCO. Okay? So why are we doing this? Well, one of the really great advantages of having all these instruments kind of clustered together is we can do science that we've never done before, that we can't do from a single platform. So we can make all these measurements from these different platforms. We'll be looking at the same air mass within 15 minutes, which is pretty much like the air mass is frozen. You can think about it that way. Cloud time scales are half an hour, 45 minutes, an hour. So if you can, all these satellites can look at the same piece of real estate within 15 minutes. You can sort of think of the atmosphere as really kind of frozen in that period, close to it. And you can get all these different kinds of measurements. LiDAR measurements, radar measurements, optical measurements, polarization measurements, infrared measurements, radiation budget measurements, everything from the same parcel. It's really an amazing kind of thing that we're putting together here. And so far we're well on the way to getting this done. So I'm going to go quickly through these and tell you a little bit about them. So Aqua was the first one that went up, and it's got an atmospheric infrared sounder. This is a temperature sounder, basically an advanced temperature sounder that looks at the infrared spectrum from about 5 to 15 microns. And it looks at water vapor, it looks at CO2, it looks at, and from the CO2 measurement it can figure out what the temperature field is down through the troposphere. It's a nadir sounding instrument that looks straight down. There's a microwave instrument associated with that, so because this is infrared, it can't see through the clouds, but the microwave component can see through the clouds, okay? Now, we also had a humidity sounder from Brazil, HSB, and it failed in orbit, so that instrument doesn't work. That's why it's crossed out. It was also a microwave instrument. But then there's another lower frequency microwave instrument, and that's producing things like sea surface temperature. And that's what this little animation is here. That's coming from this AMSR-E instrument. And what's really interesting about this is that we used to have to look at sea surface temperature on a monthly scale, because by the time we got all the clouds taken out of the picture, we were looking at it from a temperature sounder, infrared temperature sounder viewpoint. It took us about a month to get all the clouds out, and temperatures are changing. There's really subtle changes in sea surface temperature we'd miss. With this instrument, we look right through the clouds and we can measure the temperature of the ocean directly every single day. And that's what's going on here. So you see this temperature fluctuation. The other big instrument on this is called MODIS, the Moderate Resolution Imaging Spectroradiometer. And it's a very 500 meters resolution instrument which it can make measurements of ocean color and land biomass, all kinds of things, clouds and aerosols. It's a Swiss Army knife sort of instrument. You can pull out a spoon, you can pull out a knife. It's all kinds of things to everybody. And this ocean color measurement here is being made by MODIS. Ocean color is basically a measure of the phytoplankton volume or carbon volume in the surface waters. Well, you know that. I mean, it's very simple. You look at a turbid, green, scummy water, you know there's a lot of organisms in it, right? If it's blue and clear, you know that there's nothing living in it. That's basically the idea, okay? And so you can sort of see here where a lot of the growth of phytoplankton is. See it up here in the northern regions? When the sun comes back, there's a lot of nutrients in the water, and the sun is shining a long time. You get a lot of phytoplankton growth here, same as in the Antarctic. And then you have the upwelling regions off of the Galapagos Islands in Peru here. You can sort of see those, and you can see upwelling here in Namibia, off of Namibia. You can see some elements here. This is climate change in this region. So you can really see, and look at the sort of oceanic deserts out in the Pacific, sort of where Hawaii is. Out here, there are really very few fish in those regions. There's nothing for them to eat. So you have these, you have most of the fishermen want to spend their time. Look at up in here, this is where a lot of our fish come from, where the weed is North Atlantic. It's a very productive region. So Aura is the mission I work on, and it's basically a composition measurement. So we measure atmospheric composition, which means aerosols and the chemistry of the atmosphere, both the stratosphere and the troposphere. It's a really new mission in the sense that we've done the stratosphere before, but this does it a lot better, and we're able to push our measurements down into the troposphere and actually measure air quality and air pollution from space, which has never been done before. And it consists of 4 instruments, a microwave instrument which points out the front. This spacecraft is different from the other ones that you see. Mostly they just look straight down. We've got a couple of those. But we also have instruments that are called limb sounders, the atmospheric limb. We look out on the horizon and we scan downward along the horizon until we hit a cloud. Or we have a microwave instrument, we go right through the cloud and keep going. Okay? And that has some advantages in us able to get much finer vertical resolution in the stratosphere and tropospheric layers, as opposed to looking straight down. Okay? When you look straight down, you get this sort of the total amount of something. It's like you go down the aisle of the grocery store, and at the end I give you you have a bunch of things, but I can just tell you what the sum is. It costs you $50 to go down those aisles. What did I buy? Well, I don't know, it's all added up to $50. In a limb sounder, you can go down shelf by shelf and figure out what the hell it is. So it's really a cool way to do it. And we have 2 limb sounders, one pointing out back and one pointing in the front. And so within a few minutes, they make measurement of the same air mass. So MLS is a microwave instrument that scans down, and HERLS, which is an infrared instrument scanning down. And then we have 2 nadir sounders that also look down. One is OMI, which is an instrument from the Netherlands that's basically measures the column of ozone and can measure aerosols, and TESS, which can actually measure ozone in the troposphere, work it out to some extent. And it's a very difficult measurement because it has to see through the stratospheric ozone layer to do it. So it's a very high technologically challenging instrument. And here's I have to show you some results because I'm very prejudiced for this spacecraft. This is actually a measurement of NO2. And what you're looking at here is, I don't know if you can see Michigan here, Lake Michigan, and this is Wisconsin. I'm sorry, this is Michigan. I got my state wrong. Wisconsin's over here. This is Michigan. And this red indicates high values of NO2. Okay? And NO2 is a precursor for tropospheric ozone. In fact, this is on January 29th, which is unusual for a winter day to have this kind of air pollution event going on. And there actually, ozone alerts were issued for this region during this stagnant air mass. And this is what we see from space. We see this NO2, this precursor for ozone, building up in this region. We were able to see that from space, which is really new. No one's ever done that before. And look at the East Coast. You see all the pollution developing on the East Coast here. So we can do this every day. We get pictures of air pollution around the world every day from this instrument at about a 20-kilometer resolution. Now I'm going to go on to the next element of the Atrium, which is CALIPSO, which stands for Cloud Aerosol LiDAR and Infrared Pathfinder Satellite Observation, which is a made-up name. Ever heard one? But basically, this is a big laser. Eye safe, of course. If you looked up in the middle of the night and looked at it, you would not be destroyed. Unlike the Death Star in Star Wars. But this is the telescope to look at that faint spot on the ground, and it's got a 2 wavelength polarization sensitive LiDAR. This is in the green, this is in the infrared, and it provides 30-meter vertical resolution for profiling aerosol clouds. Well, why do we care about that? Well, one of the reasons that we're having trouble predicting air pollution is we really don't know the height of smoke plumes around the world, and where these aerosol plumes are, and how they vary with altitude. And that's important because we don't know the height, we can't figure out how they're going to be transported by the winds. So when you look down, you see smoke, like in the picture I showed you, but what altitude is that smoke at? Is it 5 kilometers? Is it 2 kilometers? Where is it? We can't tell by looking down. So this is an instrument that will tell us exactly what the altitude is. And also the height of clouds, knowing the height of clouds tells us something about how they were made, their properties, and how they're going to radiate in the infrared out to space. There's a lot of issues with clouds and climate models, something we do a poor job of predicting in climate models. So what we're trying to do in all these missions is narrow down all the issues associated with climate prediction, kind of squeeze the modelers into paint them into a smaller and smaller corner, and have them address the various issues and parameterization schemes in their models so we have it right. So we can make valid climate predictions instead of people laughing at us, which sometimes they do, and justifiably so, because some of our parameterizations are pretty bad. But this is why we make these measurements. We have to ground truth them. And this is an example of LiDAR taken by the ICESat mission. ICESat wasn't really designed to do this, but it was able to. It's kind of a bonus in space, and this shows what you're doing is you're flying along in these tracks, 1, 2, and 3 here, 1, 2, 3. And you can see the height of the cloud here. This black is the shadow of the LiDAR. It can't penetrate the cloud, but it gets some information about, and these are high tropical clouds. These are sitting at 16, 17 kilometers in altitude. Extremely high. You know, a normal aircraft, if you take an airplane from, say, here to Japan, the highest it'll ever get, an airliner, is this high. These clouds, way above, these are tropical clouds, they're way above the airplane. If you ever fly across the equator, you look up at these clouds, you don't look down at them. They're tall, and they're injecting water vapor into the stratosphere. They're producing a lot of nitrogen dioxide in the cloud as a result of lightning. They're very important for the energy budget. I showed you those pictures of the energy budget of the Earth, and these tall clouds are those blue regions in the tropics I showed you that are radiating to space. So this is a very important measurement, and these are some examples of the kinds of things we can get with this measurement. CloudSat is a cloud radar in space. The first radar we put in space to do meteorological measurement was on the Tropical Rainfall Measurement Mission, TRMM. And what it does is measures rainfall from space, and it was so successful in measuring tropical rainfall, we're going to continue that measurement with Global Precipitation Measurement Mission. But what we learned from that mission was that all the radars that we have on the ground are all calibrated differently. So what we did was, by flying this radar, the precipitation radar, over all these radars you see that when you go to look at your weather cloud precipitation radar on the TV, every one of those radars that NOAA puts in, the NEXRAD radars, are all calibrated differently. And if you try and use that data to work out things like energy budgets of the Earth or precipitation, they'll all give you different numbers. By flying that radar in space, we use it as a calibration standard to fix all these radars to have them all calibrated the same. This is going to be the same thing with CloudSat. It's a very interesting idea. They're going to have a radar in space to look at the structure of clouds. This is a similar type of radar called EDOP, and they can penetrate down and look at sort of the glaciation layer, where you have water below and ice above. They can sort of see the whole picture of cloud convection. They can't see small particles, but that's where the LiDAR comes in. The LiDAR can see these small particles around this. So we'll get this really good picture of clouds. Well, why do we care? We don't really understand cloud structure over the oceans. These land radars cloud radars just sit over the land. We have a few ships, but we don't really understand cloud structure over in ocean systems or in remote regions like the polar regions. And those clouds, we really don't know how to deal with them very well. our parameterizations are very poor. So this is a kind of a cool mission that's going to be right next to the LiDAR, flying right behind Aqua. Now, it isn't going to be easy, and the reason I put this slide up is to show you the kind of problems we're going to face. Here's a cloud. These are the various nadir footprints, that is the footprints on the ground of all these different measurements. So I've got, for example, here's CloudSat, these blue squares here. Okay, these are the LiDAR spots for Calypso. This big gray thing, circle, is AIRS, which is the nadir infrared sonar, which we're going to be very dependent on to see what's going on. This big gray circle. This is Polar. I showed you Polar. This is the French instrument here. It's these big squares. TESS is the tropospheric emission spectrometer from Aura. And this is MODIS running along here. So, these are like the 5 blind men grabbing the elephant. Who's going to be picking at what? They're all going to have to reconcile this cloud with all these different views of the cloud. And underneath this is a map of the Washington, D.C. area. So this big thing shows how big this footprint is. One dot from AIRS covers the entire Washington, D.C. metropolitan area. It's going to be a very difficult challenge for NASA scientists to figure out how to reconcile everything from the A-Train. But we have a lot of smart people, so we can do it. So let me give you just an example, just 2 examples of why the A-Train is really important. And I can give you 100, but here's just 2 of them. What are the aerosol types and how do the observations match aerosol, global emission, and transport models? So that's a good science question here. Calypso gives you the aerosol height information, Aqua, MODIS, and Polar and Aura only give you the aerosol size, distribution, and composition. So using all that information, we can look at global emission and transport properties of aerosols. That'll give us enough information of that. How do aerosols contribute to the Earth radiation budget and climate forcing? All of these guys above, plus the Earth radiation budget measurement and CloudSat for latent heat release, will tell us about climate forcing. Remember I said that aerosols can modify clouds. It's called the Toomey effect, from a guy named Toomey who's now retired from University of Arizona. Pointed out that that aerosols make cloud droplets smaller, they'll have less latent heat release, there'll be less rainfall. So you got to work on all these problems at once. And remember why the focus on aerosols? It had the biggest uncertainty in our climate forcing parameters. So we're really driving this whole system toward understanding aerosols and the Earth's radiation budget better. So I'm going to change a little bit here to NPP. This is the polar orbiter, the next generation polar orbiter. The current POEs, which we call polar orbiters, the reason we have, if we have geostationary, why do we need polar orbiters? Well, geostationary orbit is 36,000 kilometers from the Earth. Polar orbiters are 700 to 800 kilometers from the Earth. What does that mean? From a geostationary orbiter, it's like holding a basketball out at arm's length and looking at the Earth with your eye. Well, yeah, you could see it, but you can't get very good horizontal resolution. Okay, maybe 3-5 kilometer resolution. It's interesting, and you can't get the poles. It turns out you can only get plus or minus 60 degrees. You can't really see the poles because the angle's too steep. Okay, so we need something else that's closer in that can make temperature measurements and temperature sounding and possibly do other kinds of things down close to the Earth, and that's what the polar orbiters do. They can cover the Earth in one day. They're in what we call sun-synchronous orbits, which means they have the same overpass time locally all the time. As the Earth is turning underneath the satellite, goes around at a period which is chosen such that it's always flying over at 1:30 local time, wherever you go. Okay, for example. It could be some other time, but 1:30 is a good example as any. Okay, so we want a sun-synchronous polar orbiter. This is proposed to be 824. We may move it down a little bit. Launches 2008. And it basically has the same instruments that Aqua has on it, almost, except for this one, which is the follow-on to the OMI instrument on Aura and the TOMS instrument. So, but this is a microwave sounder that's like AMSU, this is like AIRS, and then it's going to have a MODIS-like instrument on board. We're having some trouble with this, building this instrument right now, so the mission's been delayed to 2008. It was supposed to launch in 2006. So this is sort of life in the satellite game. You get these delays and you get budget cuts. And just sort of show you what we do with, these are the two instruments that they're being built. This is the CRIS instrument, which is infrared sounder, and then you have a microwave sounder. Why do you have both kinds? The infrared sounders do a much better job, a much smaller footprint. It's much easier to get a small footprint than the microwave sounders. They have a bigger footprint. The microwave sounders have the advantage of being able to see through clouds. Okay, so the combination is really powerful. Ozone mapping. This is the OMPS instrument. This is a follow-on now to the TOMS instrument that's going to be on this system. And this system will be taken over. NPP is a test satellite that's going to be moved over to the NPOS system that NOAA's going to fly for the next 20 years. So this is the test bed. And this is VIIRS, which is basically like MODIS and can produce high-resolution pictures of ocean color, vegetation on the earth, clouds, aerosols, and that sort of thing. So it's a very nice